Have you ever realized that you've actually never touched anything in your entire life? Like physically?
Yeah, it's a wild thought.
Right. I mean, when you sit down in a chair or type on a keyboard or even clap your hands, you are not actually making physical contact.
Not at all.
At the microscopic level, you are hovering a tiny fraction of a millimeter above those surfaces, violently repelled by this invisible scaffolding of force.
It really is the secret operating system of the universe. I mean, we walk around thinking reality is made of solid objects, but it's really this complex architecture of fields and charges that are just continuously negotiating with each other in empty space.
And today we are mapping that architecture. We're going to explore the invisible forces that literally shape our entire physical reality.
Yeah, we're diving deep today.
We are. We're basing this deep dive on a really fascinating presentation titled Part 10 Electric Force and Fields.pptx. The mission here is to trace this phenomenon from the absolute tiniest subatomic interactions all the way up to the continuous fields that dictate how everyday objects behave.
So we're really looking under the hood of reality itself.
Exactly. Okay, let's unpack this. I'm opening up slide one right now, which is titled The Invisible Geometry of Electric Force.
And look at that subtitle, From Subatomic Charges to Continuous Fields. That really sets the philosophical tone for us. We're looking at the secret architecture of electromagnetism here.
So, explain this visual to me. We've got this red positive charge, a blue negative charge, and these lines flowing between them. It sets the stage, but what are we actually looking at?
Right. So to understand this properly, we have to start with the fundamental vocabulary of this geometry. When we talk about these forces, we're dealing with two main subatomic players.
Protons and electrons.
Exactly. Protons carry a positive charge, that's your red sphere, and electrons carry a negative charge, the blue one. And those sweeping lines you see flowing through the void between them.
They look like magnetic field lines around the Earth.
Yeah, very similar, just scaled down to the size of an atom. Those lines are the actual pathways of force. They are literally telling particles how to move.
But those pathways aren't just, theoretical math on a page. Clicking over to slide two, we actually see this grounded in the real world.
Oh, yeah, the classic hairbrush effect.
Right. You run a plastic comb through dry hair, and suddenly the strands are flying everywhere, standing completely on end.
So before you start brushing, both the hair and the comb are electrically neutral. They have an equal balance of protons and electrons,
Oh, okay.
but the friction of the brush moving through the hair physically forces some of the negatively charged electrons to just abandon ship. They migrate from the hair right onto the plastic comb.
It's essentially like a subatomic bank transfer.
That's a great way to put it.
Yeah, because no new money or, no new electrical charge is being created out of thin air. The funds are just changing accounts.
Exactly. The comb suddenly has this surplus of electrons, so it becomes negatively charged. And the hair has a deficit of electrons, leaving it with a net positive charge.
And because every single strand of your hair now share that exact same positive charge, they become sworn enemies.
Right, because the fundamental law of electric charges dictates that like charges repel. The strands are actively trying to escape each other's electric fields. That's why they stand up and push apart.
That bank transfer concept ties directly into slide three, actually. Looking at this picture of Thales of Miletus.
Yeah, the ancient Greeks were on this way early. Thales was observing static electricity back in 600 BC. He was rubbing amber and watching it attract feathers.
So humanity noticed this thousands of years before we even knew what an electron was.
Oh, absolutely. They didn't know the mechanics, but they knew the rules. Which brings us to the conservation of charge. If you calculate the net charge of the hair, say it's a +3, and add it to the comb, which is a -3, the total system still equals 0.
Because charge cannot be created or destroyed, only transferred.
The universe keeps a perfectly balanced ledger.
Which explains the real world static shock visual here. We've all shuffled across a carpet in socks and gotten zapped touching a doorknob.
Right, that zap is the invisible geometry violently trying to re-zero its ledger. Your body builds up a static charge from the carpet friction.
And when you reach for the doorknob,
Yeah, when you bring your hand close to a neutral conductor like that metal doorknob, those pent-up electrons jump the physical gap through the air to rebalance the system.
and that shock is just your nervous system registering the rapid discharge.
Exactly.
But that brings up a really crucial distinction. Let's call out the transition to slide four here. This is where these concepts build modern real world devices. Why does the charge jump to a metal doorknob, but not to, like, a wooden door frame.
That comes down to the materials themselves. The notes break this down by introducing Fermi energy gaps, which essentially act as gatekeepers for electrons.
Okay, so this defines conductors, insulators, and semiconductors.
Right. To understand the Fermi gap, think about how electrons live inside an atom. They exist in bands. The valence band is where they're normally anchored. The conduction band is a higher energy state where they can break loose and flow as a current.
Okay, let me try an analogy. Is the Fermi energy gap basically a bouncer at a nightclub?
I like where this is going.
Like the valence band is the line waiting outside on the sidewalk, and the conduction band is the dance floor inside. So the bouncer's job is deciding if electrons can migrate from the valence band to the conduction band.
That is a perfect visualization. So let's look at a conductor like copper wire. In a conductor, there is no gap. The valence and conduction bands overlap.
So there's no bouncer.
No bouncer at all. The line outside spills directly onto the dance floor. Electrons migrate freely.
Which is why metals carry electricity so well.
Exactly. Now look at an insulator, like the wood of that door frame. In an insulator, the Fermi energy gap is massive.
The bouncer is a 10-foot tall brick wall.
Right. No electrons are getting inside, which inhibits the flow completely. But the most important one for real-world devices is the semiconductor, like silicon.
Which has a small gap, right?
Yes, a small gap. The bouncer is there blocking the door, but he can be bribed with a little bit of energy. You get this controlled flow. And that controlled flow is the foundational principle for every modern electronic device. Smartphones, computers, you name it.
Moving us to slide 5, I really want to see how these electrons actually jump between objects. The slide contrasts two processes, conduction and induction.
Right. Touch versus no touch.
Conduction makes total sense. You physically touch a charged rod to a neutral sphere, the electrons jump over, and now the sphere is charged.
It's charging by physical touch.
But I have to push back on induction because it looks like a magic trick. How can a charged rod force two attached neutral spheres to completely separate their positive and negative charges without ever touching them?
It's super counterintuitive, I know.
Yeah.
It relies on a phenomenon called polarization. Imagine a highly negative rod approaching those two connected metal spheres.
Mm-hmm.
Because they're conductors, the electrons inside are free to move. As that negative rod gets close, its electric field pushes the mobile electrons inside the spheres as far away as possible, like repels like.
So the electrons physically flee from the near sphere into the far sphere?
Exactly. They crowd into the furthest sphere. That leaves the near sphere completely drained of electrons, making it overwhelmingly positive.
Wow.
Now, as a single system, they're still neutral, but the charge is polarized. It's segregated.
And here's the trick, right? While the rod is still hovering close by, holding that segregated state in place, you physically pull the two spheres apart.
You trap the charges. You permanently trap those electrons in the far sphere, and the near sphere is stuck with a massive deficit. You've created a positive and a negative object without ever making physical contact.
That is incredible. Okay, progressing to slide 6, I promise you, the listener, we are not going to get bogged down in textbook math here, but we do need to look at the mathematical engine of this electric force, Coulomb's law.
It's the gear turning the whole system. The formula is F equals K times Q1 times Q2, divided by R squared.
So we're multiplying the two charges and dividing by the distance squared.
Yeah, and what's fascinating here is that denominator, the distance squared. It's an inverse square geometry of distance.
Meaning the force drops off significantly as distance increases.
Right. If you double the distance the force doesn't have, it drops to a quarter.
Yeah.
But it works in reverse too. It grows exponentially as charges get closer together.
And flipping to slide 7, this brings us to a fundamental forces showdown. There is a direct comparison between electromagnetism and gravitational force here.
Yeah, this is where it blows your mind a little bit. Both forces share the exact same inverse square geometry. They both use that 1 over r squared rule.
But gravity is attractive only while EM is attractive and repulsive.
Exactly.
But here's where it gets really interesting. The staggering difference in their relative strength. Electromagnetism is about 1137th the strength of the strong nuclear force. But gravity, it's a minuscule 6 times 10 to the negative 39th power.
That is a decimal point. 38 zeros and then a 6.
It's nothing.
Gravity is a rounding error at the atomic scale. Electromagnetism overwhelmingly dominates. The tiny chemical bonds in your coffee cup easily overpower the gravitational pull of the entire Earth.
Shifting to slide 8, we can see this 1D electric force in action. It walks us through a step-by-step calculation visually. We have two charges, a positive 25 nanocoulombs and a negative 75 nanocoulombs, separated by 3 centimeters.
And Coulomb's law spits out a final force of 0.019 newtons.
Right. But looking at this, since one charge is 3 times stronger than the other, shouldn't one pull harder?
It feels like it should, right?
Right.
Like a truck playing tug-of-war with a bicycle.
Yeah.
But the conclusion from the slide clarifies this beautifully. The forces are of equal proportion but opposite direction.
So it's a perfect balanced interaction regardless of the size disparity.
Exactly. Because the equation multiplies the charges together, the forces are...
Okay, advancing to slide 9, we are adding a dimension. We're moving from a 1D line to 2D coordinate systems. When do forces cancel?
Imagine an x and y axis. You have two positive charges on the y-axis, one top, one bottom pulling on a negative charge sitting out on the x-axis.
So they're pulling diagonally.
Right. And you have to break that diagonal pull into vertical y components and horizontal x components. What's beautiful about the geometry here is that the upward pull and downward pull are identical.
Meaning the y components perfectly cancel each other out to 0?
Exactly. The negative particle isn't going to drift up or down, only the x components, the horizontal ones, add up. So they pull that negative charge straight along the x-axis.
Okay, moving to slide 10. This is the core of today's mission, understanding how fields actually function. The slide defines the electric field, or E, as electric force per unit charge.
Yeah, we're moving from just particles to the actual space around them.
I like to frame the field as this intermediary or an invisible messenger between particles, because how does a particle know another one is there across empty space?
It interacts with the field. And to measure that, we use the test charge framework. If you drop a positive test charge into a space, the electric force and the electric field point in the exact same direction.
And if you drop a negative charge in, they point in opposite directions.
Exactly, which makes visualizing them really consistent.
Which is exactly what we do, clicking over to slide 11. The geometry of interaction. We're looking at electric field lines.
These are imaginary curves that point in the exact direction of the vector. For isolated positives, the arrows radiate outward. For negatives, the arrows point inward.
But the visuals get really intense when they interact.
Yeah, if you look at attraction, unlike charges, the lines reach beautifully across the void to connect them. But for repulsion-like charges, the lines violently bend away from each other. You can see the tension.
But how do we scale this up? Transitioning to slide 12, how do we go from single subatomic dots to real continuous objects?
Because real objects aren't just single points, right? They are continuous charge distributions. The slide shows a 1D line, a thin ring, and a 2D non-conducting disk.
And the math here gets pretty gnarly, lots of integration. But to summarize it for everyone listening, integration is just nature's way of seamlessly stitching together trillions of tiny point charges into everyday shapes.
That is a brilliant way to put it. You're just adding up billions of microscopic forces to get the macro field.
Moving to slide 13, we look at a specific shape interacting with one of these macro fields, an electric dipole.
A dipole is just a positive and negative charge connected by a distance, like a little subatomic dumbbell.
So this dipole is dropped into a uniform field, meaning the field lines are running straight across the space. The forward pull on the positive end perfectly cancels the backward pull on the negative end.
Right, which means the net force along the x-axis is 0.
So my question is, if the net force is 0, does it just sit there doing nothing?
No,
No.
it doesn't move left or right. But because those opposite poles are on different ends of the dipole, they cause a rotation. It spins.
Which is known as torque.
Exactly.
Advancing to slide 14, calculating the twist, we see the step-by-step math of this rotation. The slide proves the net force is 0, then calculates the dipole moment, and applies a cross product using the sign of 35 degrees here to find the torque.
And the core takeaway here is that this math isn't just numbers on a page. The cross product perfectly represents a physical, twisting force happening in empty space. It's the object fighting to align with the field.
Wow. Okay, we've reached the final slide. Slide 15, synthesis. Let's walk through these blocks. We have the material, which is the band theory, then the particle, which is Coulomb's law.
Right? Then the field, which is the space itself. And finally, the geometry, which is the macro integration we talked about.
It's all connected.
It is. If we connect this to the bigger picture, the slide's conclusion is really powerful. Electromagnetism is not just a formula. It is the invisible scaffolding dictating the shape, motion, and interaction of all matter.
So, to wrap up this deep dive, the next time you get a static shock on a doorknob or use a semiconductor powered smartphone, you are interacting with this vast, invisible geometry of forces.
Yeah, and I want to leave you with a final thought to mull over. Building on that text from slide 15 about fields shaping interactions before contact occurs.
Okay.
If electric fields dictate that particles fiercely repel each other before they ever physically touch,
Hmm.
are you ever actually touching anything in your daily life? Or are you, in everything you hold, just fields of force hovering infinitely close, forever held apart by the very scaffolding of the universe?
Just fields of force hovering infinitely close. I love that. Thank you so much for joining this deep dive. We will catch you on the next one.
See you next time.